Nice. Hmm. I can't see how many people are live watching right now. Let's see. Cool, 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 cool. Is there a live count somewhere? I don't know. Just says waiting. Oh, okay. Yes. Hello, everyone. Uh, yeah, welcome to ML Study Jams, brought to you by GDSE, presented by me, Siddharth Shrivastava. So, essentially, in today's Study Jams, I don't know if you attended Dave's Android Study Jams, but essentially, we're going to start off with the basics. Um, so, this is session one of the three sessions. So, in the first session, we're just gonna go over it's the first session is gonna be very math heavy. So there will be a bit of maths involved once you begin with machine learning. So that's what I'm gonna be explaining. This just sort of to give you an overview of what's gonna happen and what's gonna go on once you actually start diving into machine learning. Right. So I think oh okay. I can see the chat. This is very weird. Yeah. So in machine learning, yeah. So give you an overview. So in the beginning, we're gonna go over what exactly is machine learning. Then we're gonna go into what types and what fields of machine learning are there, and then yeah, and then we're gonna see sort of what you can do with machine learning as a practical example. So we're going to dive into something called gradient descent. Gradient descent, arguably one of the most important algorithms in machine learning. Uh, I think it's fair to say it's one of the backbones of everything machine learning related, at least in modern machine learning. And then once we understand gradient descent, we're gonna dive into this fun little project. I think you can see a little preview of it over here in this tab. We'll just switch over and I'll demo it for you. But yeah, Chatram is saying, okay. Yeah, so I think enough people are here. Yeah, let's dive into it. What the hell? So to begin, try to ignore that GIF I put in there. Yeah, to begin, what is machine learning? So Google defines, so the first thing when you ask a question like that, what is machine learning? You Google it. And according to Google, machine learning is defined as the use and development of computer systems that are able to learn and adapt without following explicit instructions. By using algorithms and statistical models to analyze and draw inferences from patterns in data. Okay, that was a lot of nerdy words. Let's try to break this down and let's try to understand what that actually means. The use and development of computer systems that are able to learn and adapt. Okay, so what is the learning part exactly, and what are these patterns? So, so we have data, right? And a lot of the times in the real world, you get raw data. So let's say for today's, actually we'll do that later. We'll keep it as a last thing. So let's say you have a lot of image data, right? Let's say you take a bunch of pet pictures. You're taking pictures of your pet dog. Your friend is taking a picture of her pet cat. Someone has a pet gecko. I don't know. There are a lot of pictures. But now you've got like a whole dump of them. Okay, you don't know which picture is which. You just know, yeah, yeah. So I will teach you how to make a machine learn, right? So essentially, you have all this data now. All these pictures are data for you. What can you do with it? So one thing you can do, and we're gonna get into the depth of it later, is something called classification. So let's say you want to find the difference between a cat and a dog just by looking at the image. Now you, as a human being, you can very easily tell that okay, this is a cat and this is a dog just by looking at it because you've learned it over time. But turns out that is very hard for computers to figure out the difference between a cat and a dog. Like, okay, let's see. A cat. Let's look at this. Now, once you look at this cat, you'll probably find some features in the cat, right? Like, okay, it's got like sharp ears, got a small, cute mouth, it's got whiskers, it's got big eyes. And compared to a dog, oh my god, that's a cute dog. Yeah, compared to a dog, you look at this, and it's also got sharp ears, but it's got a bigger mouth, its tongue is out. And like, how do you explain to a machine that, okay, this is a dog and this is a cat? Like, you can either write like a whole bunch of if statements, like, okay, if this pixel value is like this, if this pixel value is like this, because obviously images are a bunch of pixels, right? And a dog, this pixel is like this is like this is like that. And you can write all those if statements. But now you run into a problem. What if you have this picture now? This picture and this picture, both pictures of dogs, but completely different, right? Like, this dog is small and cute, and this dog is looks like he could mess you up. And you can't do that with traditional if statements, right? You need the machine to sort of learn the difference. That, okay, this is a puppy, and this is a cat. This cat looks very mean. Yeah. How do you do that now? So you'll have to dive into machine learning. You need to make the machine learn. You need to make the machine learn exactly what it means for a cat to be. So maybe you start uh, training a machine learning model. So training essentially means teaching, right? That, okay, I need you to figure out, okay, that a cat has this feature, a cat has these kind of ears, and then you need to further learn, like, okay, this kind of feature, what does that mean? Okay, this sort of pixel has this kind of pattern, because that's what humans do, right? We recognize a pattern. So that's what we're sort of forcing a machine to learn those patterns. So that's essentially what we're trying to do. So what comes off as trivial for most human beings is very challenging for machines. On the flip side, machines can do huge, gigantic calculations in milliseconds, right? But for humans, those huge, gigantic milliseconds is very hard. So it's sort of like balance, right? What we find very trivial, like, let's say, voice recognition. If your mom is screaming at you, like, hey, get off your bed and do something, you will automatically understand because you've learned the language over the time. But once you give a machine like a audio file or whatever, the machine isn't automatically going to recognize that speech and understand that, oh, okay, mom wants you to get off the bed. Like, it won't be able to translate unless you explicitly teach what each syllable translates to in English or whatever language you're trying to transcribe to. So that's what machine learning is. Without explicit instructions, by using algorithms and statistical models. Now, statistics comes into play here because you're sort of trying to generalize. You're sort of trying to figure out a pattern, right? And statistics is all about like the probability of this pattern sort of existing in a given sample. So you're sort of trying to draw inferences from patterns in data. Right. I have yapped a lot about machine learning. So now let's actually dive into what you can do with machine learning. This is a lovely image that design told me not to put, but I put it anyways. So what can you do with machine learning? So as I said, there's a lot of things you can do with machine learning. There's a lot of things you shouldn't do with machine learning, but you can, just for the sake of it. So what can you do with machine learning? You can do something called supervised learning. So supervised learning is essentially a subclass of machine learning where you've been given labeled data. So now let's say I want to learn the difference between cats and dogs, right? So in supervised learning, I will be explicitly telling the machine, that, okay, here are images of cats, here are 40 million pictures of cats, and here are 40 million pictures of dogs. And now you're going to tell the machine, figure it out. I've told you what is what. You just need to learn the mappings. And when I give you new data, when I give you 20 million more pictures of random animals, you need to be able to tell the difference. So there's a lot of stuff we can do for that. So as I said before, classification. So that whole telling the difference between two classes, that's called classification, right? As the name suggests. And like I said before, speech recognition. You are explicitly telling. So let's say you take a word, supervised learning, right? Supervised learning. It's got like a bunch of syllables. So you will break down each single syllable in the speech. And then you're going to label that syllable itself. And then you're going to send it to the machine learning model. And you would hope that the machine learning model would sort of learn the mappings and figure out the word on its own. So that's supervised learning. There are various other things you can do with supervised learning. So let's say, for example, uh, yeah, I don't know. I'll think of something and get back to you. I am massively underprepared. Yeah. So then you have unsupervised learning. As I mean, if you have supervised learning, then it's pretty logical to assume that you're going to have unsupervised learning. What does unsupervised learning mean? That means now I have cats and dogs, but I'm not going to tell you which one is which. You, as in the machine. I'm just going to say that, hey, here are a bunch of pictures. Figure out the difference no matter what you want. You're not even going to be having the labels. I'm not going to tell you which one is which. You just have to figure out that there is a difference. And, here it is. So a good application of unsupervised learning is recommendation systems. So let's say you're on Netflix, right? You're binging your random summer romance flicks or whatever. And a bunch of people like you are watching the same thing. But you're not explicitly sort of telling it like, okay, this is what I want. People around you watch the same thing, and the back-end people at Netflix, the machine learning people sort of train the algorithm in a way which sort of figures out clusters of people that, sort of like the same thing. And it figures out like, okay, maybe these kind of people like the same thing. And they recommend you systems based on that. Because the user isn't explicitly saying that, okay, I want this, right? The recommendation system automatically learns that, okay, this user wants romance movies or like drama movies or whatever people are into. So that's unsupervised learning. As you can see here, there's something called anomaly detection. So now you have a bunch of, so let's say you're running like a cybersecurity system, right? And you have a bunch of users currently on your system, currently on your website, let's say. And most of the users behave normally. Most of the users are fine. They're like, okay, we'll just come to your website, we'll buy your stuff, and then we'll leave. And that's the normal sort of cluster, right? That's the normal behavior. So it figures out that, okay, these are the normal people, and anyone outside of that, so like an outlier of that sort of behavior, that learned behavior, if anyone is outside that, that means they're an anomaly, and you sort of detect that. So a popular algorithm for an example of unsupervised learning is called k-means learning. Recommendation systems can come under supervised learning as well, but I believe, one second, let me finish this k-means clustering thing. Yeah, so as you can see here, this is unlabeled data, right? But you can see, let's just open this in a new tab. Screw it, whatever. So now you have these clusters forming here. And some of these, I mean, you can tell with the naked eye that, okay, these are similar. So you will group them together using the algorithm. And then let's say a new data point shows up somewhere here. Then it'll automatically be able to classify that, okay, this is this class that I've learned just now. To answer these, I might be wrong actually. Yeah, recommendation system, unsupervised learning, using unsupervised learning, right? Yeah, no, it is the Unsupervised learning. Right. Building a okay, you can check this out later. But yeah, no, it's unsupervised essentially because the user isn't given explicit information about their behavior, right? Their behavior is what's the learned class. So essentially, that's the I'm sorry, that's the cluster you're sort of trying to learn. So now you can do this like this example here. You can do this with your naked eye because it's just two dimensions, right? But oftentimes, and 99% of the time, machine learning deals with multidimensional data, right? Multidimensional is like you have, so for an example, let's say you're trying to predict temperature, you're trying to predict the weather, okay? And you have lots of weather data available. So you have temperature, you have humidity, you have wind speed, you have UV index. And that's in many categories. Yeah, categories does not matter, Deep, because anyways you're gonna classify it, right? Like even in this example here, in this K-means clustering example, you have multiple classes, right? These are multiple categories of behavior. Yeah, in Netflix. So those are genres. We're talking about user behavior itself, like what classes the user is interested in. And that's the sort of clusters, I keep saying class, that's the sort of classes that the machine learning model is responsible for learning. Yeah, so your question is valid that in the sense that there are multiple genres and the user will pick the genres, but you don't know what else the user might be into. So again, since the user isn't explicitly giving you the label for what class they want, it's just based on like stuff they've clicked on, right? So that sort of makes it unsupervised learning. So we'll get into that later. So we have two more sessions planned. Just keep that in mind. Um, Essentially, machine learning in unsupervised machine learning, you sort of don't give them labels. That's the only difference. That you just tell the machine to figure it out. And lastly, arguably one of my favorites, I don't do this very often because it's very hard, but reinforcement learning. Now, reinforcement learning is it's super interesting. I don't know why I'm geeking out about this right now. But reinforcement learning involves, so if you've ever heard of DeepMind, let's look at DeepMind. No, I'm sorry. Deep Brain was it? Something deep chess, what? Something like that. Alpha Mind or something. Deep Blue, right. Deep Blue. So Deep Blue was a chess playing expert system that once upon a time beat Gary Kasparov. And then this was essentially like just a rule based system that was successful in beating one of the best chess players of all time. But then came Alpha Zero, right? So then came Alpha Zero. Now, Alpha Zero is a prime example of reinforcement learning. So, so usually when you bring up reinforcement learning, you often think about game playing agents, and you think about like yeah, essentially game playing and robotics and autonomous systems in general. So a bit of backstory about Alpha Zero. Alpha Zero. Let's actually, screw it. I don't want to open the Wikipedia right now. But yeah, so Alpha Zero was an AI system that was successful in beating a lot of the chess experts, and it was very good at what it did. So let's just open the Wikipedia, anyways. So Alpha Zero, December. Yeah, so Alpha Zero was trained solely to play via self-play. So what Alpha Zero did was it played against itself. It played thousands of games against itself and figured out the rules and figured out the best way to play the game of chess. Now that is very impressive because imagine you are trying to learn chess, but the only thing you can do is play against yourself. And the only thing that you have is a feedback mechanism, like a feedback loop for learning. So let's say I'm trying to learn chess and I moved e4, e5, d4, d5, whatever I did. And then I lost. Okay. I was trying to make white win, but white lost. I did some random moves and I lost. So in reinforcement learning, you usually get a fitness score. So if you lose, that's a bad fitness score, which means that you have to try something else. And then that's what you sort of have, right? You reinforce your learning. You said, okay, I am messed up. I need to do something else. I messed up. I need to do something. Oh, I did something right. I should do more of this. So let's say the after like thousands of iterations, the AI finally figured out how to checkmate. Okay, it finally figured out, and then that from there it can learn that okay, these are the best strategies for checkmating people. These are the best strategies, and then it went on to play against like a lot of people. So it played against other chessbots that were already uh, sort of established, and it was very interesting because yeah, even in other games like Go, which some people argue that it's a lot more complex than chess. Only after 34 hours of self-learning, AlphaGo Zero won 60 games and lost 40. Like it was so good that it was beating professionals uh, who had been playing for years. So there was another story. I don't know if you've heard of the game called Dota 2. Dota 2 AI, right? So yeah, so OpenAI itself, OpenAI, creators of ChatGPT, our favorite chatbot. OpenAI built a bot that could defeat Dota 2. Dota 2 is a video game. It's like a strategy based MMO type game. And only after like a few months of training, I think it was able to beat professional video game players who had been playing for like 9, 10 years. So this was sort of the proof of concept of reinforcement learning. Reinforcement learning had been going for a long time. IBM had been making like those Atari bots that could play like old Atari games and win against them. But essentially, what happens in reinforcement learning? There's a mechanism. We don't have to go in this further. I'm just showing it to you. Yeah, so as you can see here, there's a reinforcement learning model where you have your agent, that's your bot, and agent performs an action in your environment. And you get a score, you get a reward, and you get the state, the current state, like what has changed in the environment. The agent has to learn that. And then based on the reward, the agent will change its actions. And then it'll repeat until you get like a significant amount of improvement. So that's been reinforcement learning. And let's see. Yeah. So that's sort of the types of machine learning that we're gonna see here. These are the three most common ones. I should really close that out. Yeah, these are the most common types of machine learning we see out. I mean, there are more examples like I don't know, we'll see. Like there's something called representation learning where you try to convert something to something else. You use autoencoders, blah blah blah. We don't have to dive into that right now. Uh, so now gets into what is in it for you. Okay, you as in the viewer watching. What are you gonna need for machine learning? This beautiful field of computer science that we have. Well, unfortunately for math haters out there, you're gonna need maths. Okay, you're gonna need a lot of maths. Specifically, you're gonna need probability. You're gonna need statistics. You're gonna need linear algebra, and you're gonna need calculus. So today we're gonna dive deep into calculus. There's gonna be a lot of calculus. I'm really sorry. So if you got bad grades in your calc papers, I'm sorry. So did I, but yeah. So yeah, these are the four major fields in machine learning that you need. Like these are just the bare basics to understand what's going on under the hood. And now since we're programmers, at least most of us, we're gonna need programming, right? To implement those algorithms that we write, those learning algorithms, you're gonna have you're gonna have the first mathematical representation, then you're gonna have to like translate that to machine language, right? So that you can automate it. You can apply that mathematics into whatever you're trying to do. So, yeah, I mean, let's see, calculus. So, I don't know. I think you're gonna need like calc one portion. What in calculus one? Yeah, I mean, like you're gonna need limits. You're gonna need estimating values. Calc two. So you're gonna need a lot of. I don't know if you remember like those optimization problems. Like, yeah, like you have to solve integrals. You have to you figure out sequences in series. I mean, all this not that much. Differential equations probably. And yeah, and then calc three. You come up with vector calculus, I believe. Yeah, so multivariable calculus is gonna come in clutch for this one because, like I said before, you're gonna be working with a lot of multivariable data, right? You're gonna have multiple data columns, let's say, features in your data, and you're gonna have to optimize your algorithm based on all those features. So to do that, you're gonna have multiple variables and therefore multivariable calculus. It might sound scary because it is, but if you get into it slowly, you'll figure it out. I'm sure. So now we should see what we're gonna do for this session. So the motivation for this session essentially was me. I am a broke college student. I do not have money. Like my parents will give me, but I need to start making money eventually, right? So a good way to make money. I was watching certain movies online, Wolf of Wall Street, for example, and stock markets is a great place to earn money. I thought to myself, and I was like, you know what? I don't know anything about trading and stocks and investing. I don't even know where to go. But what I do know is how to write code. So what I can do essentially is make a stock prediction bot, right? Because you have all this data. So let's say Google stock, and you have all this data available to you. Like you can just take this data, you can download it, and then you can do whatever you want with it, right? So once you have data, you can pretty much do anything because at the end of the day, it's just numbers. And numbers means maths, maths means statistics, and statistics means you can predict what's going to happen next, right? If you have historical data, you can predict future data. I mean, in theory, that's what we're trying to explore here. So I got this data. So today, for our that's the code for our linear regression. I'll dive into linear regression in a bit. So what we're gonna do essentially is we're gonna make a very simple stock prediction bot. Let's say stock prediction system. We're just gonna show you. I'm just gonna show you the underlying mathematics of what's gonna happen, what we're trying to do. So we're gonna use an algorithm called linear regression. Linear regression. Right. Now, linear regression, it's arguably one of the easiest things in machine learning, at least the way we're going to do it. I mean, there are easier algorithms out there, but this is what we're going to do. So let's say this here is our, this is our stock. Okay. This is just the rudimentary data points. Our stock is moving up. It's fantastic. Now, what is going to happen next? Okay, this is time, this is price, X is time, Y is price. What's going to happen next? You don't know. I mean, you can eyeball it like just by looking at the data, but the name of the game is machine learning, right? You're going to make a machine figure out, okay, what's going to happen next. So here you have linear regression. Linear regression, essentially, you try to fit a curve. So now fitting a curve essentially means that you need to find a line y equal to mx plus b, a line that is closest to all the points that are present in your data. And once you figure out that line, once you figure out those two variables, y equal to mx plus b may, you have m and b, right? Those are the defining features of your model. For example, our model right now is this line, right? You're trying to figure out the best line that will fit this, um, that will fit the following data. So how do you do that, right? That's what we're trying to figure out here today. So now, once you have this line, let me just explain further. Once you have this line, all these points are historical data, and what comes after that can be predicted using the line, right? So in theory, that's what we're going to do. So if you go back to the Google stock, yeah. So let's say this was today's Google stock, and we start sort of analyzing. Okay, from here to here, we can see from our naked eye that, okay, it's going up. So we should sort of fit a curve. Oh, sorry, yeah. We should fit a curve that would sort of predict something called a trend, right? In the long term, for our case, it's just one day. But in the long term, where is this data going? Cool. How do we do that? So let's keep, oh, yeah, okay. Never mind. So we're going to do something with this data set right here. It's the master card stock price. I should probably have this ready, but whatever. Yeah. So this is our data. This is our raw ones and zeros or whatnot. It's not ones and zeros. It's just like what you have for stock prices. Is this it? Yeah. Yeah. So this will be our data that we will load into our system. You have date. You have like a whole historical, like you have from 2006, 25th May to 2024, 25th January. Like, oh my God, it was updated a day ago. Yeah, this is very recent. So anyways, you have open price, high, low, close. Now, I'm not a stock trader or whatnot, but essentially, volume is, I think volume is like the number of shares traded that day or something. I don't know. I'm not a finance person. I'm a programmer person. Okay. So now, essentially, the feature we're interested in is close, right? At what value the price is going to end that day. What is the end price? So that's the value we're interested in. So that's what we're going to try and learn. So we're going to plot it out, and then we're going to figure out how to learn it. Now, that's the source of our data. We're going to try and predict where the MasterCard company's stock is going. So here I showed it to you already. I don't know why I'm showing it again. But yeah, here we're going to try and figure out the distance from each. That's going to be, I'm going to explain it later. It's called the error, the mean error or whatnot. So how good or bad our sort of curve is doing depends on how far it is from the data points, right? So the way we're going to do that is literally just we're going to initialize a line randomly, like it is going to have a random m and a random b, and then we're going to check the distance of those points, of each point in the data set. Every single point from the data set, we're going to check the distance, and then we're going to sort of sum it up, and then we're going to say, okay, this is how bad our line is doing currently. We need to improve upon it. So now let's get into meat of our learning part. So this is the main algorithm we're going to be diving into. So you have linear regression, and linear regression is dependent upon gradient descent. What does that mean? Gradient descent. So now this is going to get very mathy. So I suggest you take out a pencil, paper, whiteboard, whatever. But gradient descent, here we have gradient descent is an optimization algorithm of finding a local minima for a differentiable function Gradient descent in machine learning is simply used to find values of a function's parameters that minimize a cost function. Keep that in mind as far as possible. So there's a lot of stuff that I've just said. Let's try to break this down. Gradient descent, first of all, is an optimization algorithm. What are we trying to optimize? We're trying to optimize the closeness of the line, closeness of the line with the rest of the data points. And how are we going to do that? We're going to find a local minima of a differentiable function. We'll get into that shortly. Gradient descent in machine learning is simply used to find the values of a function's parameters. So right now, our parameters are only two. Y equal to mx plus b. Y equal to mx plus b. So we're going to get into the code very shortly. Just hold on. I think it's going to be a very short session. I think 45 more minutes and we'll be done with this. But yeah, so y equal to mx plus b. I think all of you remember this from like 10th grade. I don't know. I can't remember. But yeah, so yeah, rise over run. You know all this. Y equal to mx plus b. That's what we're trying to do here. Right. So now, what do we do with that? Those were our two parameters, right? Our two coefficients. Now, cost function. Let's get into what the cost function means. Cost function essentially means how good or bad your current model is doing at whatever it is you're trying to make it do. So right now, we are trying to predict where the stock will go. Now, if this line is very, very far from the other points, that means it has a very high cost, or it has a very high error, you could say, because it's not doing what we're supposed to do. So now we need to minimize the error, right? The cost function is a function of the parameters that you give it. Cost function is dependent upon the given data, and it is dependent upon the parameters that you're currently using. So now, how do we calculate that? So here, our cost function is going to be this. MSE stands for mean squared error. So there's a lot of maths, by the way. I'll explain this. So yi and y hat I. So yi is the value when you put your point in the line. So let's go back. Yeah. So you have your line, right? Whoops. Yeah. You have your line. Now, instead of x, you're going to put the time. So if we have data till 25th January, right? We are going to put, let's say, 26th January. And now we're going to see, okay, what's the price going to be on 26th January? And we're going to get some value, and that's our x, right? X is our independent variable, and y will be the price. That's our dependent variable. So close will be a dependent variable. So now, since we can't explicitly put in dates, right? Date is not a number, essentially, which you can calculate. I mean, you can, but not in this sense, not algebraically. So instead, we're going to swap this out with like index values. That we'll figure it out later. Once we get into the code, everything will get a lot clearer. So that's the independent variable and the dependent variable, and you plug that x into the line, and you get your output. That's going to be the future predicted price. Now, our challenge becomes how to learn that, right? So now we were talking about cost function. So yi is what your line is currently giving out. Once you plug in once you plug in x multiplied by m plus b, you get yi on that particular data point. and then y hat I is the actual data point, right? So you're essentially trying to find out the difference, right? So, yeah. So you're essentially trying to find out the difference between your predicted and your uh, actual models, whatever, data point, whatever. Yeah, I'm sorry, I lost train of thought for a second. So mean squared error is gonna be our main algorithm. So now what we have to do is we have to minimize this. Now that this is where the calculus comes in. So gradient descent, if you know, you don't, I have to explain it to you. Gradient descent, you have to minimize this. Now, if you remember from calculus, what is gradient of a function? Gradient of a function. So it gets into all like partial derivative and stuff, right? So gradient of a function in vector calculus especially gives you a direction, because a vector is a direction. Gradient. I don't know. Okay. So if you remember from multivariable calculus, yeah, it gives you a direction which points to the minima of a function, right? If you remember from like monotonic functions, finding the gradient helps you minimize, like once the slope of your function is at zero, it it means you're at minimum value. So let's say you have like a quadratic function. Let's say you have a quadratic function, right? If I find the point at which the slope is zero, that means uh, that the value is minimum. So same thing you're doing here, but for multiple values, multiple features, multiple variables. Now you need to figure out the gradient, and then the gradient will give you. So I think there's a good visualization. Gradient descent visualization. Yeah. So this is the visualization that you're going to be implementing. So yeah, let's go here. Let's say this is the function. Yeah, I'm sorry. There's a lot of maths. This is one algorithm. There's so much more maths that it's gonna screw with you a little bit. But just bear with it, okay? Because it's fun, I swear. Yeah. So now let's say you have a function and you're trying to minimize this. How are you gonna do that? You're going to take a gradient. What is the derivative of this? 2x plus 1, right? So let's say you started at 0.5. Yeah, that was our setup. Right. Yeah. And learning rate, we'll get this into a bit. But the next iteration, you come closer to the minima. This is our minima, right? Right here. You make another iteration, you come closer to the minima, closer. And eventually, you've come to the minimum. So in our case, the function that we're trying to minimize is the mean squared error. How now the mean squared error is dependent upon m and b of your line. And based on the mean squared error, depending on how high the mean squared error is, you're going to reduce it down. You're going to come to a minima so that you can find optimal values of m and b. Yeah. So here is the uh, partial derivative. So for gradient, if you remember, you're supposed to figure out the partial derivatives. And then once you find the partial derivatives, you're supposed to subtract it from the original. So yeah, I don't know why that isn't. So now, you know what? Let's actually dive straight in the code because I've been yapping for way too long. I think it's time for you guys to see. Oops. The code. So please connect Colab. Just close these tabs. Yeah. Okay. Colab has connected. Runtime. How do you clear? Whatever. So now let's get into code a bit. Let me know if the text is visible. Otherwise, I can make it a bit bigger. Yeah, I think this is comfortable enough. Get out. So now we're gonna need three libraries for this, okay? And this is as basic as it gets as far as machine learning goes. In session two, we're gonna dive into scikit-learn and we're going to dive into TensorFlow. These are two major popular machine learning libraries out there. But we are not gonna do any of that this session because I want you to understand the maths and see for yourself that how much maths is gonna be involved in machine learning. So now you have three libraries, pandas. Pandas essentially helps us figure out and load in the data. It helps us play with the data set. So our data set, the format of our data set is CSV. CSV stands for comma separated value. Essentially, you can understand it as a Excel file. Okay. So our CSV file is being now handled by pandas. Pandas, great library. If you want to become a data scientist, you need this. Now we have matplotlib. Matplotlib is essentially going to help us, show pretty visualizations of our data. And you have NumPy. NumPy, arguably one of the most important libraries. So NumPy, no matter how advanced you get in your machine learning journey, you will be using NumPy. I will guarantee that. I mean, you can use like alternatives, like TensorFlow has a lot of the stuff that NumPy does built in. But at the end of the day, you're going to come back running to NumPy because it's such a beautiful library. NumPy helps you do linear regression and essentially handles all the math, right? It can help you define arrays, like mathematical vectors. It can help you do statistics, like it can help you. Where and how can we code? Yeah, so I will share the link for this. You can have this link actually. I don't know. So I'll share this link later, I guess. I didn't think we'd need it, but you can follow along right now and then I'll show it to you later. I'll make this public. It'll be on the GitHub. So yeah, once we figure out, I'll show you the maths later. Okay. So yeah, NumPy. Let's actually go to the documentation. That will help you figure things out better. NumPy. Please load. Yeah. Helps you make powerful n-dimensional arrays, numerical computational tools. It's open source, fantastic, blah, blah. Yeah, so it can run on GPUs. GPUs also, you'll figure out later, they are very important once you start like deep learning. Yeah, so here's what NumPy lets you do. Like it can help you make multidimensional arrays. Since we have multidimensional data at some point in our lives, we're gonna need multidimensional arrays. We're gonna need something called tensors. That's where TensorFlow comes in and all that. So learn, I think, let's just dive into the documentation a little bit. I won't take much of your time. Yeah, so you can define like n-dimensional arrays, you can do maths on it. You can define a range. So let's see what's happening here. A is equal to numpy.range, a range. And this goes from 0 to 15, 14, because it starts from 0 and there are 15 values. And then you can even reshape the vector into 3 rows and what is that, 5 columns? Yeah, like 3 rows, 5 columns, like that. So you can do a lot of stuff with it. You can find the number of dimensions, 2, as you can see here, there are 2 dimensions. You can find other 2 dimensions. You can do int, that's just a data type. You can find the size, you can find the type. The type of this is NumPy n-dimensional array. And then you can do a lot of maths on it. You can create an array and whatnot. You can convert Python lists to NumPy array. Yeah, you can do complex maths in it. Like as you can see here, 1 plus 0j, 2 plus 0j. J is essentially I in imaginary numbers. Blah, blah, blah. It's not showing me. Yeah, okay. And then NumPy.linear space 0 to 9. This you can figure out later. So essentially what linspace means is like, you have 9 values, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 numbers from 0 to 2. And it automatically figure out the difference you need. Like if you need 9 numbers between 0 and 2, here's how you do it. You use linspace. And then you can use like sine functions. You can even do like find the mean, median, mode, uh, standard deviation, whatever you want. Anything math related, like any math function that you need, NumPy's got you covered. That's it. Period. So let's go back. And now let's actually look at our data. So our data has been loaded into a pandas data frame. DF stands for data frame. And pandas is currently reading a stock market CSV file. I've loaded into Colab already. The steps for it are very straightforward. You can just Google it later. But yeah, so now these are our data types. These are our columns. These are our features, right? You have date, you have open, you have high, you have low, and here's what we are interested in. You have close, volume, dividends, stock splits. We are not interested in all that. We're interested in date and we're interested in close. So now let's actually now only isolate our main target variable is going to be close, right? So one second, let me just comment this out and only show you why. So why we have isolated only these values, right? 4.27, blah blah blah, and you have 3,871 values. So this numpy array that we've defined here now is going to have those many values. So we're not going to use all of the values because we only want to see the most recent. So we are going to take only the last 1500 values. So now if we see, uh, yeah, so this array is uh, this numpy array is 1500 elements big. It has 1500 numbers in it. And for people who are wondering what is norm, norm is something for normalization. So I'll explain that later. But yeah, so now here is our code. I should have cleared this before starting, but okay. Yeah. So now we'll go through this line by line. One second. Uh, actually, I think you can, Dhriti, I think I've sent the code in the group. You can just check it out and put it in the chat if you find it. I'll put it later. But yeah. Okay. Normalize index. So now this is our test. We'll do the actual stuff later. So now we need to figure out a range, right? We need to figure out the indexes, as I said. Like the first day is day 0. So you will define it as 0. And then it starts at 0 and it ends at length of y. So like the last 1500 value. And that's how you define it. That's the index, normalized index. So now norm is essentially just a number that it maps it down. So you're dividing every single index by this arbitrary constant here. I chose 17 because it was fitting the best. You can play around with it later. But norm essentially maps everything down because the highest value, if you see max, the highest value in the stock that is ever that ever appears is 394.685. But our x goes from 0 till 1500, right? So you have to sort of map that down so that it can correlate better. Okay, you can look up normalization and why we do normalization later. I'll explain it in the next session. Right now, just understand that we have normalized everything. So what's happening in this line of code essentially is you've defined a range from 0 till 1500. It's a numpy array, and you're dividing every single value in that vector by the normalization constant, which is 17 for this instance. Now we are going to define a line, right? Currently, this is just arbitrary, by the way. So our intercept, our b, is 0, and our slope is 1. And this is the equation. Oh, yeah. Thank you. Yeah, so this is the regression line. There is intercept, there is slope, and there is a normalized index. Normalized index essentially means x, right? m into x plus b. That's a regression line. And then once we plot it, we plot our data. So this is our beautiful data. This is how it looks. And this is just a random line, right, that we've sort of defined. What do we do with this now? This line right now sucks. Okay, there's a lot of error. Do you see how far every single point is? This line isn't predicting jack. So what do we do? So now let's define our data. So now x, that's our independent variable. We're defining it again just for the sake of it. But yeah, so you're doing the same thing as last time. Data, you're defining it as a list. This is just easier to understand. And then 1500, 1500x, 1500y data points. And now, I'm sorry. Now you're gonna get into the you have defined your data, like you have purified everything. You have just exactly what you need. Now let's do something with it. I don't know why I have this too. I don't know. Yeah. So 1500x, 1500y. Now this is arguably one of the most important functions. So this is our error function. Oops. This is mean squared error. We've just taken this and converted to code. This is the code version of that. Okay. So answer is equal to b plus m into data. So data index 0 is essentially our x, right? If you know Python indexing and slicing and all that, you're basically multiplying with x. That's easy. That's fine. And y is your y, right, in this function. So you're passing in data and you're comparing. So now y minus the answer, if you see here, y minus the answer whole square. That's your this portion, everything in the bracket. And then you find the mean of it. You find the average of every single. So essentially, yeah, so the whole vector. So right now, this is a vector. Every single value in that vector is being squared. And then you find a mean of that vector and you get a value back. So currently, if we check for our line right now, where we have set intercept as 0, and slope as 1, and we have given our data, our normal data, you will see that our total error is 33,341.09, whatever. So now how do we reduce that? We need to use something called, now we have another function that depends upon this function called the step gradient function. Step gradient, I mean, you can call it whatever, but yeah. So now you need to take, so if you remember from gradient descent visualization, you were taking small steps, right? To, yeah. See here, you were taking small steps. 1 step, 2 step, 3 step, 4 step, 5 step, and slowly you are converging to your minima. That's what this function, that's what this function is responsible for. So it's quite a bit of function, big function, but we'll dive into this. So you initialize your current gradient. Now, basically you're taking this equation and putting it into code. This line and this one is exactly the same. Okay, I will tell you what we're going to do with it now. So this is just a bit of indexing, like you take each point and then subtract. Now what you're going to do with this is, once you figure out the gradient, right, you're going to pass in your original data point and check it against the gradient. You're going to get a value back. You're going to get a direction of where you need to go to find the least minima, right? The local minima, as you say. And then you have the same equation. You have this equation, you've just converted to code. That's all we've done. Now, this is one of the most important steps, and this is where we introduce learning rate. Okay. So now learning rate is essentially, we have defined it here as well. So learning rate is how small of a step you want to take, right? Gradient gives you the distance, but learning rate sort of defines the magnitude of that step that you're taking to go towards the minimum. So great. So the learning rate depends entirely on you. You need to sort of experiment and figure out. Because like if your learning rate is too big, like let's say one, let's set up, let's say one, then your value will continuously jump around and it will never converge. Like no matter how many steps I take, it will continue bouncing around. Right? I'm at iteration 36 and I'm still not reaching the minimum. And I will never reach the minimum because the learning rate is too big. But if I make my step, like the granularity of it a little more, then it's very easy. Like you can see, it's just slowly going and we have converged at the minimum. Easy, right? And there's a trade-off with this. Now, let's say I made a 0.05, like very small, the learning rate. So then it'll take forever. It'll take forever to convert. I'm sorry. Yeah, it's gonna take forever. I mean, you'll get there eventually, but it's gonna take way too many iterations. So now what do we do, right? So you need to figure out, you need to like experiment with this. This is something called a hyperparameter. Hyperparameter means a parameter, like the other parameters are dependent upon this. So hyperparameters are something you set on your own through experimentation. So then you have something called hyperparameter tuning, blah, blah, blah. You'll get into this later. But yeah, so an optimal learning rate is pretty important for like the speed and efficiency of your machine learning system. So you'll have to continuously experiment with that. So yeah, so I'm sorry. So essentially, your new values will be your current values with the updated gradient. You've used the gradient to find the location, to find the direction of where to go, multiplied by the learning rate. So how big that step should be, and in what direction it should go. So now you have updated it, and you will continuously do it for every single data point in your data set until you figure out the best values. So now you're gonna do this continuously and you're gonna do this multiple times. Okay, let me just move that. Yeah, so here for our data set, I've set the learning rate as 0.0025. Okay, this was optimal after like experimentation. Here, this is an empty array. It's gonna store the error rate, right? Like right now, the error was what? 33K. You're gonna try and reduce the error. So this is just a training loop. So we are gonna do this whole step gradient stuff 10,000 times. Okay, 10,000 for this algorithm especially is not that much. So anyways, we're gonna run it 10,000 times. We're gonna update B and M 10,000 times, right? Like eventually you're gonna take 10,000 steps essentially. Like you're gonna take 10,000 steps because our data set is so big and we have two parameters. So actually let's gradient descent. There's an image that I'm looking for. Yeah. So here we have two parameters, right? Let's say J theta is our cost function and theta 0 and theta 1 can be analogous to M and B. So if you're here, let's say, if you're here, you're trying to get to the bottom of this bowl, you're gonna take a two-dimensional vector to get to the bottom of that bowl, right? So same thing, what you saw here. This is just the two-dimensional version of that because you have two parameters. Because you have two parameters, so you're trying to get to the bottom of this three-dimensional thing where the z-axis is error and the other two axes are your parameters. So you can imagine in like more than 3 dimensions, like how you can't even visualize that. So eventually there's something called like dimensionality reduction and all that. You'll get into that later. There's a lot of stuff in machine learning right now. But yeah, so now you've done all this. You're going to take 10,000 steps, 10,000 iterations to get to the bottom, to get the lowest error, right? So in the beginning, because you're starting with 0 and 1, you're gonna have a very like high error, and then as you take some steps, it's gonna get lower and lower and lower. So this is something that I've kept for myself. So if you saw here, once you set this, it sort of oops, it sort of starts overshooting, right? So this condition I've essentially kept to make it stop from overshooting. And then I'm putting the error at each interval so that I can see how the error is getting drastically reduced. So now let's run this and we can see we started here, our error was at 33,000 and it came down as the iterations went. It came down and right now our error is at 500. Oh, yeah, Abhay, Andrew NG's course is great. It's one of the best courses I've ever seen. I highly recommend you stick with that and make sure to take notes when you do. And please be very pedantic about what he's saying because he gives very detailed explanations into whatever he's saying. So, yeah, Andrew NG's course is great. Andrew Eng, I think that's how it's pronounced. But yeah, keep at it. It's great. So, anyways, so now we look at our error and we see that our error is drastically reduced. Our error went from 33,000. Someone said my paths. One second, let me explain this and then I'll get to your question a bit. Yeah. So as you can see here, our error went drastically down. We did 10,000 steps and our error went from 33,000 all the way down to 538, which means that was the sort of total distance of our line with the rest of the data points. So now this is the final portion. We can see it. This is our new line. This is what it looks like now. And that's pretty cool in my opinion, not just because I did it, but yeah, this is cool because we essentially use math to figure out the best fit path. Now if I take the future, now I have this line. The parameters of this are this and this. So if I go to Desmos, please load. Yes. Now I can plot this exact line in Desmos, and then I want to find. So we did the 1500 data points, right? Now I want to find the next day's value, which means 1501. So what's going to happen right after this, right? Like right after this line, what's going to happen? I can just put it in graphing calculator. Y equal to, what was our M value? Our M was this, copy, multiplied by X plus, what is our Y value? 74, blah, 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 plus this. Now this is essentially our best fit line. So now if I go all the way to like, Y15, I don't know how this works, but whatever. So now if I do 1501, divided, oh yeah, we also have to normalize, right? 1501 divided by 17, that was our normalization parameter. We get 524. Apparently that's gonna be our next value. Sure, maybe, possibly. So that's what our machine learning model gives us. And that's the prediction that it gives us. Like, okay, at that value, this will be our price. So now that we've done this, what's after this? Like we've spent like a 1 hour, 10 minutes. I feel like there's not much. I mean, there's a lot of detail. You can get into this, but then you'd be here all night. So for stock regression, you can now do a lot more with stock regression. You have so much more with stocks. Like it gets messed up once you start adding, like, let's say you're adding 2000 instead of, yeah, 2000 values instead of 1500. So now you're taking a bigger sort of data set. 1500, you run everything, blah, da, da, da. And then this is the same thing. The error reduces down from something to something. Yeah, and this apparently is our best fit line. You get a new different line for the last 2000 values because you've added a bit more at the end of it. So there's a lot more you can do with this. Now you can do something called polynomial regression, which means our curve will not be linear. It will be a curve. It will be a polynomial curve. Oops. Images. Right. Polynomial regression. It's not polynomials. Why is it regression? Yeah. Polynomial. So yeah, in our linear model, it's just a straight line. In a polynomial regression, you can actually fit like these curves, like it's going slightly like that. It's not fitting right because it has to be a straight line. But in polynomials, you have a bit more flexibility as to how to fit it. So you can do polynomial regression. Next session, we're gonna dive into LSTMs. We're gonna dive. I'll show this. I have like a PPT and everything. Yeah. So of course, we need more data now, right? With more data and better models. That's what I was saying, right? We need a better model. Linear regression works fine if you have like a very small data set, like how we saw right now. But once you start getting into like big data sets, like multiple features, you're gonna need a bigger model. You're gonna need a better algorithm to fit your problem. So now we're gonna use these guys in the next session. We're going to have neural networks. Neural networks, as the slide suggests, are the cool kids of machine learning. Okay. Neural networks are a very, very powerful algorithm that helps you do this stuff better. So next session, we're gonna dive into these LSTMs. Okay. I'll put it up in the group or whatever later. But next session, we're going to do LSTMs. We're going to dive into natural language processing, NLP, as they say. And yeah, so this is all the math that you require. I think a good video for this would be Siraj, gradient descent. Yeah, linear regression using gradient descent. This is a good video explaining it. Andrew Ng. Oops. Go back. Andrew Ng's course. Yeah, so Abhay. So if you want like a, what do you call it? Pathway. You have like back end. Yeah, roadmap, as they say. Yeah, so let's say you need a roadmap. You go to this website, roadmap.sh, and you have multiple roadmaps. So let's say you want to become a front-end dev, you want to become a back-end dev. For our sake, you want to become an AI and data scientist. Here's a roadmap. So in the beginning, obviously, you have the mathematics. You need linear algebra, calculus, mathematical analysis, differential calculus, as we just saw. You need gradients, you need optimization, you need all sorts of things. Then you need statistics, you need hypothesis testing, probability. The probability is fun. I will give you that. Then you get into like formal statistics like A/B testing, increased test sensitivity, blah 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 blah. You can go through this whole thing. Obviously, we've skipped a bit and we've done the coding part first because of our curriculum. Then you get into this, then machine learning. We've obviously skipped a lot, but yeah, this stuff is very good to know if you want to get into machine learning properly. So roadmap.sh. Dhriti, if you want, you can put this link up. But yeah, so roadmap.sh is a great place. If you want to become a backend dev, you can follow this guide. No matter what you want, you can just go here and check it out. This is like crowdsourced, I think. So yeah, so we're gonna figure out how to use neural networks. We're gonna use a library called TensorFlow in the next session. TensorFlow. This is a beautiful web library that will help us build neural nets, and we can figure out more robust sort of systems and bigger data sets. Uh, no, leave it. It's fine. Yeah. So roadmap to research, I think it's pretty easy to memorize as well. But yeah, so TensorFlow is what we're gonna do next for our session 2. It's gonna happen next week, Friday. And yeah, until next time, I guess. So I think we have, if we have no questions, I think we can end this here. Abhay, you still here? Okay, cool. So I feel like I should go a little more into the maths. So a good book that you can read for the mathematics of all this is the deep learning book. Deep learning book. It's available online. It's free. Yeah. So you can check out like all the things you're gonna need for machine learning, right? You're gonna need linear algebra, probability, numerical computation, machine learning basics. Then you gotta get into like neural nets and like stuff like that. We'll figure this out like next, yeah, next session. Sorry. So stick around, I guess, and yeah, for now, can we end this, Triti?